Good morning, everyone. Thanks, Rinku, for this nice introduction. We'll start with the first day today with us of the 3 days which we'll be having with you guys. So we'll get started on how to make you guys cloud ready and understand on some of the key concepts that are involved for you to deploy your application on the cloud, right? And that's what we do as day one, the day two of the full stack networking session. So, what's the agenda for today? The first session that we'll have now will talk about a brief introduction into virtualization and containers, and then we'll give you guys some time to get on board with the setups that will be required throughout the day today, right? So we'll give some time in the first session itself for that. The second session will give you a brief introduction into Docker and how the Docker tools you can use and what are the APIs you can use for the same, right? And after that, we'll go a bit more advanced into what are more advanced concepts in using Docker containers. And finally, at the last, we'll stop with cloud orchestration, that is deploying your containers on the cloud. We'll use Kubernetes as our orchestration framework, and we'll go a bit deep dive into what are the tools that are available, right? And at the end of the session or end of this day, you should be able to deploy entire your application on the cloud. That's our aim, and we hope you guys get to it, right? So as I said yesterday, please raise your hands if you get any question or get stuck anytime, because next 3 days we don't have a theory part and a hands-on part separately. We'll go as and goes. We'll teach the theory, then you'll have do the hands-on, then we'll move forward once you finish the hands-on part, right? So we good? Yeah? Please keep answering, please keep asking questions, yeah? Okay, so let's get started for the first thing. So who is here who has not watched the World Cup final? Or is there anyone here? So how many of you used Hotstar to stream the final match? Raise your hands. Almost everyone, right? So did you see the screen, and on the right side, they actually give the stat of how many users are currently watching with you. So did you notice the number there sometime? So it was how much, right? It was in crores, right? And one of the time I saw it, it was around 5.6 crore viewers simultaneously watching the match, right? So that's a huge crowd. I mean, I know India's population is large. That's a small number compared to it, but it's a huge number to manage because we were all watching it real time, right? And there was no break. It was not circling and we were not hanging. We could all see it real time. And that's a huge achievement for Disney Plus Hotstar. So how were they able to manage it? With the help of cloud infrastructure, right? So they had almost lots of CPUs, lots of GPUs, lots of memory in, very highly connected network in their data centers to enable all this large set of users to view the match in real time simultaneously, because you can't do it like with one rack, with one set of servers. You cannot scale for such a large audience that way, large user base, right? So this is a first-hand example of where you guys experienced a large infrastructure of cloud being in play, right? So a brief history of how cloud has evolved over last several years. Long back in 1950s, when there was a need for, like, okay, there is compute coming in, you needed people to use these resources simultaneously. That's when mainframes came into picture. And they were like, okay, morning, some users will use, later in time sharing basis, some applications will run one time, and after that, once it exists, other application will run, right? That was the mainframe things that were there in 1950s, right? And they were like, okay, then there was a box which was running the application. Then they were like, can we connect these applications together, right? So I want my one mainframe somewhere running, I want to talk to another guy running other application somewhere else. So can this connection be done? And that's when there was this first paper out where the ARPANET paper, which would help show that you can get devices or your machines connected and talk to each other over a network. That was the first time they said that, okay, you can get applications connected. We're like, okay, now I don't need my applications all to be running on one cloud. You can connect them across diverse locations, right? So then we're like, okay, this kind of part is handled for me. But still, the time sharing thing was a bit of a throwback, right? You have to use application. You cannot run them simultaneously at a moment. So that's the place in 1972 where they introduced virtual machine operating system. We'll go a bit deep into it today. So that's when the virtualization thing just started out. That okay, without time sharing, I should be able to run my application simultaneously and in an isolated environment. So there could be one company running their application. Simultaneously, there should be another company running their other applications. That's what virtualization enabled, right? And that's, as I said, that now they had the compute being isolated, but still running simultaneously. That's the same part they wanted in a network. You connected them, but they wanted that isolation happening in the network as well. That's when, in 1990s, virtual private networks came into picture. You have the compute being isolated, you have the network being isolated, so that enables companies to run their applications end-to-end over multiple machines that are connected in a private environment, still being a shared environment, right? With that, because multiple people or multiple companies had confidence in using these shared environments, but with that, the requirement increased, and there was a need to add more resources to it and scale it to cater to large number of companies or large number of applications that needed this shared infrastructure, right? So that's when all these cloud thing came into picture, where you would have obviously heard of Amazon EC2 or Google applications like Google Docs, which use this cloud infrastructure to run their applications. Right? So, and that's when major large-scale companies came together and decided, okay, now we need data centers to run these applications. We need a proper infrastructure where we'll have racks of servers, connected by high-speed network, good cooling system. That's to build such large infrastructure. They came together and built these server farms that were called, right? So that's where they built the server farms in 2007, around 2007, where these data center concepts came into picture. And now, okay, now virtualization was pictured, my infrastructure was sorted by these guys, but still there were some drawbacks on how they were affecting the performance. That's the time we'll see today in the first session, that there were some drawbacks when they used virtualization and they running virtual machines. And that's the time they saw, okay, we need something more lightweight, and that's when containers came into picture. And Docker was the one who kind of introduced or started containers. And then when containers came into picture, you want to scale them for cloud infrastructure. That's when you needed an orchestration platform for containers, and that's when Kubernetes got introduced in 2017. And it's kind of one of the widely or largest used orchestration framework right now. Multiple clouds, or most of the cloud companies would provide infrastructure or have this as the orchestration framework. Yeah. So any questions till now? Yeah. So as Rinku pointed out yesterday, right? So how were you building applications till now? So you get assignments in your any course that you take. What do? You just write the code, it gets running, it does all the processing that's required, and you get the upload, you show the assignment, you get the marks, right? So for assignment case, it's okay to have your all processing running together, but it's like single executable, and it is all good, but it's kind of a tight coupling, right? So it's only one of you do your assignment on your own, so it's okay to, like, if something breaks, you just go and fix it, you have control over the entire code. But think about applications like, suppose, say, your Uber application, or suppose your Amazon shopping application, right? There are so many things in picture. You have your cart, you want your the shopping page to be loaded, the search there, the address page, the payment page. There are a lot of things that are involved to just run that application, right? So you cannot have one person write the entire code, right? There are whole team, or like across geographies writing or managing this code base, or managing the infrastructure for you. right? So you cannot have this monolithic application running everything on their own. That's where you want to segregate them. That is, whatever applications need, like each individual processing unit that's required should be running individually. And that's where this concept of microservices came into picture, where you run all your one single processing separately, and they will be interconnected, talking to each other to exchange, suppose, a request or get a response, send some state across. And this is what is the basic building unit for any application in the cloud, right? So all the applications that get deployed on the cloud are microservices. That is, you have small function units, small processing unit doing the processing for single processing, right? So the microservice, each microservice does that processing. So it's easier to manage, easier to debug whenever something fails, because you know, okay, something fails, every microservice prints out logs, gives out metrics, so you can go back and pin down, okay, this log or this metric was from this microservice, I'll go and check what's wrong in it and go and fix it, right? And it's easier to scale also. So sometimes what happens is you have a database, you are sending requests to it. So the person or the microservice sending the request doesn't get bottlenecked that way, right? It doesn't face any, like it can handle suppose 1,000 requests per second. But the database in the backend, if it's running on suppose five cores and it can only handle suppose say 50 requests per second, then you want to scale just the database. You don't want to scale the microservice before it that's sending the request, right? So you want to scale just the database. So because of this microservice architecture, you can just scale the database and keep the front end that is, you have two replicas of the database running, and it will be receiving requests from a single replica of the front end that is handling the request from the client, right? So you can scale these microservices individually. So this is what helps better manage applications that are deployed on the cloud. And obviously you can deploy them anywhere because they are running in microservices, and as I said, as your data centers or your cloud, all infrastructure is all interconnected. You can run, suppose, your front end in one rack, your back end or the database on another rack on the same same cluster or under the cluster as well, and still they should be able to communicate with low performance overhead, right? So that's what cloud enables you to do. So there are some terminologies or buzzwords that you listen nowadays around cloud deployments or cloud infrastructures. So one is, what used to happen earlier was, you must have seen that you would have in your institute some racks of servers running, right? So they would be running your test app. If you have some online tests in your course, they will be running your test application or doing the evaluations that way. So earlier it was like, okay, it's better I keep it secure because I don't want someone else to read the question paper or something like that, right? I mean, this is a bit the naive example for it. It became more critical for bank applications which had financial data for multiple users that way, right? So maintaining that, what the cloud guys thought was, the banking guys thought was that, okay, I keep my own infrastructure, I maintain the racks, and maintain the compute, and maintain the network, and maintain the cooling, whatever is required to help this run my applications on the cloud, right? But what happened is it's become tough, right? If you they built infrastructure for say 1 lakh clients that way, right? And then every year you get new clients, right? And you need to handle their requirement or their data as well. So you want to scale it, right? But you build the rack, then if you want to scale it, you have to again put another rack with 10 new servers to manage the increased load. So it's a very cumbersome job to manage all your infrastructure on your own. So this was what private clouds were maintained majorly, where you ran your applications on your personal infrastructure and maintain it personally, right? So these becomes very tough to manage. That's when people were like, okay, now, okay, it's very tough, I'll move it on the cloud, but can the cloud provide me the same security or same guarantees that the private cloud was providing? And that's where all these big companies like Google, IBM Cloud, Amazon AWS, Microsoft Azure, they said that, okay, I'll give you the security, give you the isolation that is required by your applications. And that's when public clouds became more adopted, more evolved, and because of the infrastructure that they could run. Now every one of you know, right? It's that everyone runs some or other AI workload that do some personalization or do some interpretation that requires some model or some processing running, right? So they require GPUs to be running. So now with the public cloud adoption, the application developer or the suppose a bank application did not have to worry about that. Okay, I have to buy GPUs and deploy GPUs, maintain the GPUs. They could, because they were adopted to public clouds, they could directly use infrastructure that these guys put in, right? So it becomes easier to adopt to new technologies, new hardware, scale according to the demand that's required for your application, right? So that's why public cloud became popular. And now what's we are also hearing in industry last 2-3 years is where the adoption is scaling not to just a single public cloud. That is not just your banking application running on just one cloud, but scaling it across clouds. So take the example of the Amazon application. My cart can be running on one cloud. My AI workload, which is doing some personalization to give you the shopping list, which would get you a better buy from the client, can be running on some other cloud which has better AI workload support or better GPUs running, right? So with all this, there is a need to scale your application not just from one cloud, but running across cloud. And that's where multi-cloud infrastructures are being adopted or accepted now. All the public cloud providers are working towards what's needed for them to connect together so that they get best of all. Like the clients run their application on their cloud, but they can run their some other applications on the other cloud as well. Right? So just a statistic of how fast the cloud infrastructure is scaling. Just at 2022 results, it was almost so much of the applications had already moved to cloud. They are already adopted to cloud, and it's going to increase further more next 2-3 years or more that way, right? More applications are getting adopted to using public cloud infrastructure. Right, so this is all the introduction on what's there in cloud and where we are in the cloud space. Right, so let's get a bit deep into what enabled it. So I projected the evolution, and that the first thing that came there was the virtualization that enabled to run these applications in an isolated environment simultaneously. Right, so you would have run some Java application, right? So don't confuse what I'm going to tell now with that. That's what is called as process virtualization. So that means, what does process virtualization mean? You can run your application anywhere without worrying about the underlying infrastructure. That's process virtualization, which Java virtual machine kind of provides you, right? But what we are talking about is system virtualization. That is, you can run your machine over another machine. That is, if you have your laptop, say, right, it has some operating system like Windows or Linux running. You can run another machine which has, suppose, say, Windows or Linux running over it, right? So that's machine running over machine. That's what is called as system virtualization, right? So what enables it? What is enabled? Like, you have the physical machine, you have the host operating system. There is a thin layer, or there is a layer above that runs to enable that, and that's called as hypervisor or virtual machine monitor, right? Which enables to run virtual machines over the machine machine over the machine is called as a virtual machine that can run over your host operating system as well, right? And that virtual machine itself will have operating system and also the application that you want to run. So the operating system that's run on these virtual machines are called as guest operating systems, right? So what are the challenges to virtualization? So you would have studied operating system in your courses that way, right? In third year courses. So what the operating system prof would have told you is, right, operating system has the full control of the hardware resources, right? So because there is a machine running now over another machine, it has the guest operating system. The operating system feels that I should have control over the entire hardware. Right? It doesn't want to know or feel that it's running, sharing the infrastructure with another operating system or another application. Right? So that's a major challenge of how do you provide such an environment to these virtual machines. And obviously, if you're running multiple machines, the first question or every question that arises is how you provide this isolation, right? So, and how do you multiplex this? Because at the end, the physical resources that exist on the host operating system are limited, right? How do you multiplex these resources so that these applications can run simultaneously on the same infrastructure? So this is a key critical challenges that arise when you do virtualization. And there are techniques on which this is handled, or different ways in which this is handled for virtual machines. The first one is, okay, now you know there is a guest operating system running. We make the guest operating system aware that, okay, you are running as a guest and not as the host operating system. So there would be a modified operating system that runs as the guest instead of not the similar that runs on the host. So that's what is called as para-virtualization, and that is kind of common earlier, and Zen is a hypervisor which enables this para-virtualized environment. The next one was, okay, I don't want my operating system to change. That's a very cumbersome job to do, right? You cannot have operating system change to run on a VM. Right? So you can have your unmodified operating system running, but what it will take care is that there will be binary translations done in dynamic binary translations done in runtime, so that your instructions get converted to your host operating system. So the code doesn't change, the operating system code doesn't change, the binary doesn't change. It's just you need to translate every time you go give us an instruction from the guest operating system. You get an instruction from the guest operating system to the host operating system. So the hypervisor does these translations. So there are, this is a full virtualized mode where there are the common example, or the first example, or who initiated this full virtualization environment is a VMware workstation, which was the first paper which enabled or declared that you can have a full virtualized environment. But still, there were some performance issues with it, right? You do these binary translations dynamically every time. So this is a huge performance overhead to support this fully virtualized environment. So the hardware guys did some new empowering of this to enable these virtualized environments, and that the third form of virtualization came into picture, which is called as hardware assisted virtualization, where these modern CPUs let you run the hypervisor or your guest operating system in different privilege mode. So operating systems have some privilege mode running so that they can have access to the hardware, right? So the guest operating system also needs these privilege modes. These privilege modes were enabled using some special VMX mode that was called a VMX mode that the CPU supported, so that you can do these instructions and not have the overhead of these translating, because the hardware will do these handle the special mode or special privilege mode that's given to these operating systems, right? So the hypervisor that enables that is KVM and KEMU, which have a kernel module running in the host operating system that enables this translations that way, right? Enables these privilege modes running for the guest operating system, right? So as this figure says, there are these hypervisors which run above your above your host operating system, like VMware and Zen, but there are some which run along with your host operating system to enable these fast translations for the guest operating system. Example, the KVM, right? Any questions till now? Okay. So, because you have so many layers running, the question comes in, okay, you have the host operating system, you have the hypervisor, you have the guest operating system. Can I get the same performance that I was running when I was running on my physical machine, right? So if you run some application on your laptop, you boot up a VM, run that same application, will you get the same performance? The answer is no, right? Because there are a lot of translations that go in picture to get that instructions in or get that input, the IO in, right? So it required a new research thread or new research challenges in picture to do these optimizations for the virtualized environments that is running your application on the VM, right? So some optimizations that happened. The first one was like we'll talk in bit detail on this one, that is IO virtualization. That is how can you let your requests coming in and requests going out, that is the receive and transmit of your packets at a high speed even in the VM, right? So how do you do that? We'll go a bit deep into that today. The other two is memory virtualization. In memory virtualization, you have a page table in the operating system, right? And because there is a guest operating system, there is another page table that your guest operating system also maintains. Then there needs to be a mapping between the guest operating system and the host OS operating system page table. So how you optimally do it with the help of some hardware support for memory, so that these translations are not done every time, and there is a copy of that guest operating system page table maintained at host, so that the lookups are speeded up, that memory lookups are speeded up from the host side, right? So the other which optimization that was done was for CPU. That is, as I mentioned earlier, the hardware assisted virtualization, right? So hardware like CPUs evolved themselves to support some privileged instructions or privileged modes to run your guest operating system, like the VMX mode to run these guest operating systems in some separate privileged mode than what's supported by your host operating system, right? So we'll talk about IO virtualization, right? So in IO virtualization, as we said earlier, in any virtualization thing, the guest OS thinks it has control over the resources. And so it also assumes it has control over the IO devices as well, which is not the case, because there are intermediate layers like the there's a host operating system in place which has actually the control of the IO devices. So how do you make sure that you give the operating systems that are running as guests good access or fast access to the IO devices, right? So there are two commonly used techniques to do IO virtualization. The first one is emulation, where wherever there is a read or a write happening from the application, that is application runs a system call that, okay, I want to send a packet. Then that's a read system call that gets given to the guest operating system. Then the guest operating system needs to do that on an IO device, but when that instruction goes down from the guest operating system to the host, to the hypervisor, it traps there, so that the IO can be done by the host operating system without the guest operating system knowing that someone else is doing that IO for it, right? So we'll, with a figure, understand how this emulation works. And the other one is direct IO, where you need your physical NIC. That is, as I said, for hardware-assisted virtualization, the CPUs had some privileged modes running so that they could support this virtualization. In the similar way, the network cards also evolved to support virtualization, and so that you could slice the NIC, so that there would be one slice given to each of the VM or each VM running on the guest on the machine, right? So that's what is called as device IO and direct IO, and we'll study about that also in a bit, right? So there are many optimizations that are there to optimize the IO, but we'll study just two of them in today's session, right? So how does IO happen in a emulated mode, right? So as I said, in emulated mode, there's no hardware support that we have. We have to do all that translation from the guest operating system to the host operating system in software. So what happens is, as you see, suppose the guest application here as point 1. So the first, as we said, right, that the guest operating, the application needs to send a request, right? It wants to write a packet out of it, right? It just wants to send a request. There's the user system, it makes a system call which goes into the guest OS. Now guest, oh, I moved the slide ahead. Okay. The application makes a request, it goes to the guest OS, right? So guest OS, when before, as it says to the kernel module running as a hypervisor in the kernel, that I need to do a IO, that I need to send a packet out for the application running above me. What it does is it lets the guest OS exist, so that okay, I'll take control of what needs to be done for the packet for your application, right? So that time what it does is there is, so as you can see here, there is a root mode, there is a VMX mode. This VMX mode lets the guest OS run on a privileged VMX mode ring 0, right? Here that's ring 0, which is where the guest OS is running, and this is the KVM is running at the ring 0 of the kernel, right? So what it does is it actually switches from ring 0 to ring 3, where there is a user space process running, that is KEMU, which what it does is, okay, which is handling all the requests for from guest operating system. That is for the hypervisor. There is a user space component running with KVM, which is running on the kernel. There is a user space component running in the user space to handle these requests from the guest operating system, where what it does is it has multiple CPUs assigned to it, right? So what it does is that request goes to what is called as vCPU0 in KEMU, where the KEMU process has multiple CPUs, and that's the first CPU where the request goes to, and it says okay, it's a IO request. So IO request can be blocking as well, right? So if you send the request, you have to wait till the response comes back. So you cannot have your operating system hang, right? Because you have kept your, as you know, we have kept the guest operating system in a hanging mode till all this processing is going on. So you cannot keep it hanging till the reply comes back, because there will be some other application running on your guest operating system which will need it to do the processing, right? Your operating system cannot hang. So what else does it? It spawns another IO thread, right? So this IO thread, what it does is, what this IO thread gets assigned for each request that comes from the operating system for IO, and this IO thread is the one which will do the further IO processing. That is, this is the one which will contact the kernel in the host operating system and do the IO operation, right? So by the time this IO one, the vCPU's job is, that's it. It needs to spawn the IO thread, give the request that needs to be processed by the guest operating system for the IO, so the host operating system for the IO, and then it can say the vCPU can resume getting in more IO requests from the guest operating system, right? And also simultaneously, what it does it says that okay, I have an IO thread that's blocking for your request, but you can go ahead and resume your operation. So this sixth point, that is, it informs the get operating system that okay, now you can not block, go ahead, do the further processing, and whenever I have another request like response coming in, the IO thread will notify you and that will be returned to you, and it can give it back to the user, right? So this is how IO request processing happens in a VMX mode, where there are privileges assigned to the guest operating system, right? So as you can see, there are multiple copies happening, right? So guest operating system says to KVM, okay, I want this request to be handled, then it gives back to KEMU, where it's again handled, and then again there will be copies involved when that is processed by the host operating system, right? So there are multiple copies or multiple overheads that are happening for just one request processing in this case also. So there are some optimizations done in the in this mode, in this emulated mode. Yeah, but it requires the page tables and all, right, to map it actually. Huh. Right, so it require, because it's handling for the guest, right? So it has to run in that user space mode to get access to that guest page tables. Otherwise it won't get access. Right. So the optimization that was done to avoid all these copies that were happening is to run a shared ring that would be shared across the multiple modes, that is between KEMU as well as the guest operating system. And this shared ring did not raise the request every time. That is, every time the packet came in, it didn't do all these copies. The guest operating system directly copied it into this this ring, and not immediately got absorbed or processed by QEMU. There is kind of a batch processing where once the batch gets filled, the entire batch goes to QEMU. It spawns the IO thread for that batch, and then the process comes back, and the output again gets written back to this ring, which gets consumed by the guest operating system to write it back to the application. So this shared ring prevented processing each and individual request every time. It prevented copies that were happening from the guest operating system to the host operating system. Right? So this was kind of the word IO optimization with this shared ring that came into picture in this emulated environment. Right? But still, as you see, this is all in software, so there are something involved, you have to batch, there is some delays involved, right? So you still require some fully isolated environment without these overheads as well, right? So there is some that requires some support from the hardware, right? So as I said, CPUs got optimized to support virtualization. You needed the NICs also to be optimized to support virtualization, and that's where this direct IO or device pass-through came into picture. Most of the servers that we have today in the data centers, in fact, in your servers that you have in your universities as well, have these special NICs which support slicing of your NIC. What it has is, what it will have is you have your NIC on which there will be your physical machine, physical OS running, right? So there will be maybe some application running there also, and then above that you will have VMs running. So you want this NIC to be shared not just with across all the VMs, but with applications running on the VM also, but applications running on the host operating system also, right? So for what they did is they provided what is called as physical functions and virtual functions. So these physical functions get assigned pinned to directly the host operating system. So whatever requests are coming for applications that are running directly on the host application, that got handled by the physical function. And these virtual functions, that is the slice of the NIC, got assigned to the guest operating system directly. So whenever a packet comes at the NIC for a virtual function, it directly got transferred or given to the guest operating system without the host operating system being involved, right? So there's no copies, nothing involved from the host side. It directly got the packets directly into the guest VM, right? So what it provided was these copies were avoided, and also the processing was faster, right? You had that actual operating system feel that guest OS wanted. It had the control of the physical resource also with this, right? So how does this segregation happen, right? So how does the NIC decide which request goes to which virtual function? So there is what is called as receive side scaling. What it does is it takes the 4 tuples of the request coming in and identifies based on the 4 tuples to which virtual function it should get to. And once this it puts it on the virtual function, you've already assigned this virtual function to a guest VM. So based on that, it gets assigned to the guest operating system, right? So now that what you've done is you've removed the processing that was happening at the host operating system for your IO requests, right? But there are still some performance issues because now you've virtualized, provided the physical access to the NIC, but your other instructions, that is your CPU instructions, and still are run on a virtualized environment by the guest operating system, right? So you needed, and there is a stack processing, the network stack processing still happens in the operating system of the guest, which requires some VMX mode transfers, right? So there's this new concept that's supported by Intel that's called as Intel Data Plane Development Kit, or DPDK. What it says is, okay, you've got the access to the physical NIC, right? I'll provide you a driver where now that you bypass the guest kernel space as well. You get the packet directly in the user space of the application so that there are no more further copies involved in the guest operating system as well. And with this driver, you can directly get that packet to the application without any copies. There is zero copy transfer from the NIC directly to the application, right? So what it does is, it has a ring that is running in the user space, which maintains pointers to memories where the packet is stored. That is what is called as RT membuff, is where packets is stored, and the pointer to that exists in the RT ring, right? And all that is in a huge buffer, which is called as RT mempool. And the whole point of having these whole memory pool is to avoid cache misses. That is, every time you don't want to have you want to cache miss when you want to process or get a packet, right? So you maintain a huge memory pool for this application, and whenever the packet comes in, the pointers are also in that same memory, the packet is also in the same memory. Use the pointer, get the packet, process the packet, and send it across, and that will go out from the virtual function that got assigned to your application or your VM, right? So these are some of the optimizations that came into picture for virtual machines. And but as you said, whatever it is, it cannot defy the fact that there is a guest operating system or another software running. There is a hypervisor running in between. There is a guest operating system running in between. So there are some instructions which would require some transfer across, and some memory accesses have to go via these, right? So there is some overhead involved till now with the guest operating system also and the hypervisors, right? So the question that everyone asked was, can we make this a bit more lightweight? Can we reduce the overheads that I'm facing with my application running on a VM? And the answer was yes. This concept existed in kernels long back, but they got adopted to provide this isolation just when people started seeing the disadvantages that they were having with virtual machines, right? So what you have is, you have the hypervisor running over the physical machine and running the VM. Like OS already provides this running of parallel things, right? You have your processes running parallelly on your operating system as well. So can we leverage what that concept was to provide this isolated environment for the application as well? And that's where containers came into picture, where you don't have a hypervisor running, you don't have a guest operating system running, you have the application running directly on the host operating system, but you provide this isolation guarantees that the application requires, right? The same isolation guarantees that virtual machines provided. You wanted the same isolation, but without the overhead of the hypervisor and the guest operating system, right? So how do you provide these isolations? There are two major what I can say, two major catch points that are there, the kernels that are available today. One is namespaces, right? So we'll go in deep in the next session in that. I'll just briefly touch on the topic. What namespaces do is, they provide an isolated environment of the resources. So at the end, what isolated environment is, I want to run a CPU without another container or another application looking at my instructions, what are running for my application. What other resources involved is network, and other resources memory or disk, right? So all these resources can be isolated using these namespaces, so that in this name only applications or processes that are running in that namespace have access to these resources, right? So namespace is the technology which provides this isolation that's required. The other thing is, okay, I provided the isolation, but then the question is, what hypervisor provided along with the isolation was that the VM that was got created, it asked for so much CPU, the hypervisor took care of that, it did not exceed the resources that it had asked for or it was allocated, right? So that resource guarantees that were required, and so that no other virtual machine that is running could hog my resources, that isolation, guarantees were provided by the hypervisor, right? So you needed similar guarantees in the container environment, and that was given using C groups. C groups limits the amount of resources that can be assigned to your container, right? So it makes sure that if a container tries accessing some more resources than which were allocated to it, it just crashes that container. That is, okay, you were not allowed, or there was a limit that was set to your container, and you are not allowed to use more than that. So C group takes care of that resource level dynamically. So with these two insights into the kernel, this container environment could handle isolated environment with resource guarantees and would run your application that you were earlier running in your virtual machines. Right? So with this, you could run your applications on cloud in a container environment. Right? So how do you run the containers, right? So you had a hypervisor, I agree, right? So it was handling a lot of stuff for you. So for a container environment, how will I manage creation, deletion, updation of these containers? So there is a technology called as Docker, which takes care of all this for you. And what it does is, it provides you a toolkit where it will be easier for you to create your applications to be running as a container so that they can be moved across machines without any changes, because it has it provides an environment where you can have in that container whatever is required for processing your application. Whatever you have some dependencies, right? Okay, my code will run only on Python so and so version, or Go so and so version. So if I want that guarantee that I don't care about what Go version is running on the host machine, I want to take care that okay, only that version is used. So that packaging of your application plus your dependencies into one image or one environment is what is provided by Docker, right? So it's supposed that ease of portability because of that. And you will see in the next session that it's once you get hang of it of how to create these Docker containers, it's very easy to create and deploy it, right? So obviously it's easier to create and deploy it, and along with that, as I said earlier, it provides isolated environment that container supports, right? So what are the components involved in Docker? So what it has basically is a Docker client, which is kind of the API that's exposed to you, right? And you'll see in the next session, you'll use these APIs to create the Docker containers. And what it does is, once a client request comes, it goes to what is called as a Docker daemon, right? So what it does is, the client requests come through the APIs, it goes to the daemon. The daemon takes care of all the resources for you, like it creates the namespaces, it creates the C groups that's required, creates a network, the shared memory that's required, all that is handled by the daemon. And along with that, it handles the networking also that's required for your containers, right? And we'll see in the next session that you need to package them into one environment, right? As I said. So how you package it together and where you store it is where it's stored is what is called as Docker registry, right? So this environment that is required for your container to run is stored as an image in this Docker registry, right? And at the end, obviously, with all these things handled, you bring that container up to be running on that physical machine, right? So with this, I think kind of done with the initial introduction on virtualization and containers. Just a last slide on saying that is the Docker the only tool which enables containerized environments? No, there are multiple tools available, but Docker is a runtime that's widely used in most of the orchestration platforms right now, right? So and another reason for that is because of the daemon that comes with it. It's a lightweight daemon that comes in Docker, which provides you the support of creating all these resources and namespaces that are required in an isolated environment, right? Which is not provided by some tools like Codman, if in case you've heard of that term somewhere, right? So with that, stop the talking part now. I think I spoke a lot and without asking you guys some questions. So this other part of the remaining session, we'll use for you guys to install Docker, because the next session we'll do hands-on. Like Kavya will talk about some tool, you'll have to install it, and we'll only move forward when you have the tools or commands running on your laptop.